Okay, Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam Malaysia Madani. Terlebih dahulu kami ingin memohon maaf atas sedikit technical issue yang menyebabkan delay selama 10 minit. Untuk memulakan majlis, ada satu serangkap pantun untuk semua. Tinggi-tinggi pohon cemara, setinggi tiang istana raja. Salam pembuka awal bicara, selamat datang kepada semua. Saya, Myzairah Hamdzah, selaku moderator pada hari ini. Bagi pihak pengajar, kami amat mengalu-alukan kehadiran semua ke sesi webinar Hub Malaysia kali ke-16. Sedikit info berkaitan program webinar ini. Dianjurkan setiap 2 bulan oleh Pusat Pelestarian Alam Sekitar dan Sekuriti Air atau lebih dikenali sebagai IPASA dengan kerjasama projek Global Challenge Research Fund Water Security Hub untuk berkongsi pengetahuan tentang isu-isu berkaitan alam sekitar dan air kepada semua termasuk komuniti, pelajar dan juga pihak industri. Untuk makluman, IPASA mempunyai lebih 10 orang Felo penyelidik yang terdiri daripada pakar dalam pelbagai bidang dan kali ini izinkan saya memperkenalkan penceramah webinar yang juga merupakan salah seorang Felo penyelidik IPASA iaitu YB yang bersara Profesor Engineer Dr. Idris. Beliau merupakan Profesor dalam bidang kejuruteraan kimia bioproses. Beliau juga mempunyai lebih 30 tahun pengalaman dalam bidang penyelidikan berkaitan rawatan air dan air sisa, bioteknologi alam sekitar, penapaian dan beliau juga mempunyai H-index lebih daripada 37 dan mempunyai lebih 5,000 sitasi. Beliau juga merupakan pengasas dan pengarah spin-off company Memtech. Tanpa membuang waktu, dipersilakan Profesor Engineer Dr. Idris untuk menyampaikan webinar yang bertajuk Penyelesaian Mudah Kepada Masalah Air. Sebelum saya memberikan webinar ini kepada Profesor Idris, ingin disampaikan sedikit makluman kepada para hadirin. Jika ingin bertanya, bolehlah menulis soalan anda di ruang komen Facebook dan kami akan membaca soalan tersebut ketika sesi soal jawab di hujung webinar nanti. Okey, dipersilakan Prof.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat datang kepada webinar yang ke-16 ini. Terima kasih saya ucapkan kepada Puan Moderator for the very kind remarks introduction. Dan juga saya mengucapkan selamat datang pada para hadirin yang ada di sini. Tajuk hari ini ialah saya ingin berkongsikan sedikit pengalaman saya dalam penyelidikan saya dan bagaimana hasil penyelidikan itu boleh diaplikasikan untuk menyelesaikan sebahagian daripada masalah air. So antara beberapa projek yang saya akan terangkan ialah salah satu daripada projek yang saya baru selesaikan mengenai rawatan air, treatment of water in glove manufacturing process. Air yang dirawat daripada factory glove from one of the leading glove factory companies. Okay, next slide please. So saya akan bagi sedikit introduction apakah kaedah yang kita gunakan dalam projek yang beberapa projek. Saya sebenarnya nak tunjukkan beberapa projek, saya tak tahu sama ada video saya akan boleh lihat tak, nanti we'll look into it. And then I will also look into saya akan fokus pada satu industri projek yang baru saya siapkan, and saya akan go through the details of the project, macam mana kita mula pada awal dalam testing the whole testing of the water in the lab, dan bagaimana kita upscale sistem kita ke dalam sistem yang lebih besar. Okay, next please. So the title of saya punya project ini, particular project ialah kita want to treatment of the glove manufacturing plant effluent using hollow fiber nanofiltration membrane and also a foam fractionator pre-treatment. So the hollow fiber nanofiltration membrane ialah membrane yang telah kita hasilkan melalui penyelidikan kita beberapa tahun yang lepas. Dan so kita nak gunakan this membrane kita dalam menyelesaikan masalah yang dihadapi oleh syarikat glove manufacturing ni yang menghasilkan air sangat banyak. As you know that industry, next slide, as we know that the glove industry ni is an industry yang banyak menggunakan air. Why saya kata industri glove ni banyak menggunakan air? Sebab dia terdiri pada 3 proses. Bila kita nak buat glove ni dari 3 proses. Satu ialah you call it the cleaning process of the former. The former is what you call it as the former as the glove mold. So the first treatment is to do a cleaning process of the former. And then the next step is to actually to form the gloves onto the former. And finally is the cleaning, the leaching process before we actually before we take out the gloves from the former. So dia ada 3 peringkat lah, and in every of this single process and any of these processes dia melibatkan penggunaan air yang sangat banyak. So as you can see down here, the former is actually attached to this a conveyor system that moves from one tank to another. So the first tank they move is the acid tank, and then in the acid tank they remove all the dirt, and then after that they will go into a rinsing tank, and then will pass into an alkaline tank to make sure that all the acid are removed. They want to neutralize the former, and then after that they go to another rinsing tank. They go to another rinsing tank to make. They go to another brushing tank to make sure that the former is being brushed, clean off of any chemicals lagi. Then they dip it again into another rinsing tank before they go into another coagulant tank. The aim of the coagulant tank is actually to coat the former to make the mold too, with calcium carbonate and also calcium nitrate, so much so to ensure that for the next step the latex will stick onto the former. So it then goes to the next step of the latex dipping, latex tank 1, dipping the latex onto the former. Then they go for oven drying. Then they go into another latex tank for the second coating, and then only they go to the third tank here, whereby you have the pre-leaching. In other words, they have to make sure that all the other proteins, unnecessary sensitive proteins, are being leached out from the gloves, so that then you will not be. Though some people are very sensitive to some of these proteins, they make sure it's leaching. The whole leaching process takes place, and that involves water again. Then go to another process of beading and so forth, and the last process also involves the rinsing of the gloves and also the dismantling of the gloves from the former. So we can say that in the process involves about 3,340 kind of meter cube per day of water, and in fact they're discharging about 1,500 meter cube per day of water into the system. So the amount of water used is extremely huge. And then we can see here that the kind of wastewater that we have actually from this rubber industry, we find that the pH is really it's about 8 to 10, and then you're talking about a TSS of about close to about 200 over 68 to 239, and top of COD, which is very high, is about 1,700, and also the BOD exceeds 388, and so all these parameters have to be removed before it is discharged into the drains, so as to meet the DOE standard B. We're not talking about standard A, we're talking about standard B. So the aim, and currently they are using, of course, next slide please. Currently the processes they use are the standard kind of in any manufacturing process. Next slide please. So our intention here is actually when we go to the company to solve the problem, our intention is actually to introduce to them to use our nanofiltration technology, which involves a nanofiltration membrane that is very capable of removing all the proteins and all the other particles. Okay, and then pass it, and what we get and here is the clean water. So you have this effluent here, passes through the membrane, and then get clean water down here. And as we know, most membrane systems are very energy efficient. They're eco-friendly, they are time-saving, it can be operated easily, you have high rejection rates of small molecules, and it produces very clean water. But the challenge here lies in the prevention of the fouling onto the membrane, and that's one of the biggest challenges that we actually have to solve, because they have tried using an ultrafiltration membrane, whereby the filtration was only runs for about 8 minutes, and then they have to do backwash for 30 minutes, and they have to repeat the whole cycle again. And they actually try to put a screening before the ultrafiltration process, but basically even the screeners get clogged after some time. So the problem now is that even if our nanofiltration works, another thing that is of a great challenge is to remove the latex before entering the nanofiltration membrane. And we want to use a very simple process without using any chemicals, no coagulation process, no precipitation process. That is what we are trying to do. Okay, next slide, please. So So the problem statement, as we know, is that we know the problems that the wastewater produce. Basically, it's actually drained off, and we want to make sure that when it drains off, once it meets the standard B, and that we want to also make sure that some of this water can actually be used back into the process, so much so that can even save the water that they use. You can save the water and also money for the company. So we know that the membrane process can remove the latex, but the only process now we are thinking of what is the pre-treatment process that is suitable, so much so that the latex can be removed at least 50 to 60% before entering the membrane process. So that is going to be our challenge. Next slide, please. So our research significance that we thought that we want to actually come up with a pre-treatment process that is capable of producing cleaner water, and it's a very simple pre-treatment process that does not use any chemicals, and we want to integrate this membrane process with the pre-treatment process. Next, please. So therefore, this is the objectives that we place ourselves, which I've already actually explained it in earlier. Once we have actually identified the pre-treatment process, then we can then optimize the pre-treatment process. So the most important thing is that we have to design and fabricate the pre-treatment process that we want, and we want to use a foam fractionator. Why we want to use a foam fractionator? Because a foam fractionator involves the use of air that can actually carries out the latex float using a simple flotation process that will then float the latex and the fine particles up onto the tower, and then you collect the clean water at the bottom of the tower. Okay, so this is our methodology. Next slide, please. So I think the literature review, I can just omit it. So the current process, I've already explained to you that usually, for example, the current process they use, most industries in the rubber industries, they use coagulation, flocculation, electrolytic, oxidation and reduction, and they use activated carbon and also fractionation process. So they have a series of processes to use before they come to the final membrane process. And some of them doesn't even have a membrane process. Of course, some of them use an anaerobic filter or an aerobic biotreatment, but that process is, as we know, is a very lengthy process. It's time consuming and involves gloves company. They want something very quick to solve the problem. Next slide, please. So, okay, just to explain, okay, we have our own hollow fiber nano membranes which we actually fabricated, and we know the size is about 2.8 kilodaltons with a nano size of about 0.38 nanometers, and then it's able to actually remove 77 to at least 80% of turbidity. It has the capability to remove about 50 to 60% of water hardness. It's capable of reducing BOD by 70 to 80% and also COD. Next slide, please. Now the next thing is that we are thinking of a foam fractionator. Why a foam fractionator? Because in this particular process, okay, we want to make sure that no chemicals are added in. Okay, so what we did was we pump in the fit inlet using a centrifugal micro bubbler pump. It's a very unique pump that when the feed comes in, it comes in the form of bubbles. Okay, and these bubbles, upon formation of these very small minute bubbles, it collects all the latex in the feed, and the latex will float at the top here. So this will be the place where the foam is collected at the top here. And what happens is that the clean water will just sink to the bottom and is collected at the outlet down here. So in order to ensure that this idea of us works, what we have to do is we run small scale experiments first. Okay, next slide, please. So in our methodology, the first part of the experiment is to do it on it to get the samples from the industry and use our small systems, lab scale systems, to actually see whether the idea that you put forward works or not. Okay, and in order to know whether the idea works or not, of course, we have to do experiments. One, we have to make sure that we run in chemical experiments to test the water, and also we check on the flow rate of the water coming out, whether they are reasonable or not. Okay, and if it's successful, then only we go to the second stage of the process, whereby we will then optimize this small scale system, so that then we can then go to the final stage of upscaling the whole system. So what I'm going to do now, I'm going to explain to you our small system first. Next slide, please. Okay, this is our this is our filtration system. Okay, when we do it on a small scale, we use a very simple module which will be fabricated and we actually design it. So you can see down here, this is the dirty water, the effluent that we're talking about, and you can see that it's full of latex. As you can see here, very high COD, very high BOD. Turbidity is also very high. You can see that once it passes through the membrane, you find that the clean water is collected down here. But we know that, if you were to use this membrane directly, it will get foul within 30 minutes. And then we have to stop, and then you have to do back washing, and then you have to repeat the whole system. And then the life of the membrane will be very much shortened. So what we do is that we then fabricate a very small scale kind of foam fractionator here, which is about 100 centimeters in length, about 30 centimeter in diameter. And we run, and we have the centrifugal microbubbler that pumps in the feed and creates micro bubbles to then break down and also form a foam with the micro bubbles. And as you can see down here, it floats the foam at the top down here, and what we get is the clean water at the bottom here. So what we do is that we then analyze the water that we get from every single stage of the process. We see that what happens when we put the effluent directly into the membrane, and what happens if we put directly into the foam fractionator, and then what happens if we combine the two systems together. Okay, so that's what we did. Next slide, please. So our research findings basically show that, okay, so these are the 4 things that we did. We have done the we characterize our membranes, because every time we fabricate our membranes, we will need to characterize our membranes to make sure that they are of the same size that we actually specify. And then we also do a physiochemical analysis of this filtered water from the membrane, output from the membrane. And then we check the anti-fouling properties of this membrane, whether these membranes, the fouling is actually reversible, irreversible, and what is the total fouling properties of the membrane. And then what we did was also analyze the water that we actually produce, one from the membrane without passing to the fractionator, and one after passing to the fractionator process. Okay, next slide, please. So after fabricating our membrane, okay, we make sure we run a series of tests to make sure that the cutoff point is at the point that we said is about 0.38 nanometers. So we are sure that that is the kind of mass-produced membrane that we produce with a size of 0.8 nano. Then we use it for the treating of the effluent. Next slide, please. So you can see here. When you talk about nano, what is the difference between nano, ultrafiltration, microfiltration? Just to give you a brief for those people who are just who are not well versed with membranes. Just say that in membranes, we have many materials that make membranes. We have polymeric membranes, we have ceramic membranes. The current system that they have in their plant was a ceramic membrane, which was fouled very easily. So our membranes was a different kind of membrane. We use a hollow fiber, but it's a polymeric membrane, and our size is in the nanofiltration range. Of course, you might have heard of the ultrafiltration range membranes, and also the microfiltration membranes, which are of a larger pore size. Microfiltration membranes are the largest pore sizes. And then you have the ultrafiltration membrane, smaller in sizes. Nanofiltration is actually a size that is in between the reverse osmosis and also the nanofiltration membrane. The size is not as small as the RO, but it's smaller than the ultrafiltration membrane. Okay, just to have an overview of when you say about membranes. So what we did was, after we test, if you were to use just the membrane filtration system, we find that, okay, this is the kind of quality that we get. As you can see down here, this is the before, and it is after. So we find that TDS is removed by about 57%. The TSS, total suspended solids, is about 97% is removed. As you can see, from 966, you can reduce up to 7. So the ppm here is very, very small, and the BOD and COD is very much reduced, as you can see here. It meets the standard B, and even meets the standard A quality. So we can meet the standard A and standard B quality. So we can actually in fact, all these are the different types, because all these are water samples from the different points of the plant. Some are after the cleaning tank, some are from the cleaning tank, some are from the leaching tank, and some are from the cooling tank. Of the most dirty water, the most dirty is the ones, it fluctuates. So usually the most dirty is from the leaching, but in this particular case, the leaching tank seems to be much cleaner than the. In fact, the leaching process usually is the part where you find most of the waste in this leaching tank, the water from leaching tank. But you can find that here that in most cases it almost meets the BOD and the COD for the standard B. Standard B. In fact, in this case, it exists because the wastewater was very bad. But cooling water, it meets all the standard. Okay, so, but what we did is that we know that if we're going to use it directly for the filtration membrane, we're going to clog the whole membrane very soon, very fast. So next slide, please. So what we did, we are interested to find out what happened if we pre-treat the whole thing. If we use a pre-treatment process. Oh, okay, before that, I want to just touch on what you mean by anti-fouling. Okay, so this is a kind of permit that we get. So we see that after running for about few minutes, to 60 minutes, about an hour, you find that the flux rate dropped very rapidly. This is because of fouling. It's very typical in any kind of membrane process. The challenge lies in the fouling process. How much of fouling can we actually reduce is the challenge in any membrane process. So as you can see here, this fouling can be due to 3 different kinds of fouling. Resistance one is due to irreversible fouling. Irreversible fouling is fouling that even after backwashing, you cannot remove them. And one, of course, you have the reversible fouling. Reversible fouling is easily removed when backwashing will basically able to remove the reversible fouling. So total fouling is basically the total of irreversible plus the reversible fouling. Yeah. So we find that this fouling process must be reduced lah. But this is the typical kind of results you get if you pass it directly, if you pass the effluent directly into the membrane process. So we know that we have to reduce the fouling. So let's check onto the foam fractionator results. Okay, next slide, please. So as you can see, this is just the details. I'm not going to go so much in detail, as you can see. So now we have a foam fractionator, and you find that in this foam fractionator is very interesting. You find that we look out for the TSS, total suspended solids, one of the most important criteria. We want to reduce, because at this foam fractionator, we know that the most important thing is to remove as much of the latex as possible, which is the total suspended solids. So if possible, you want to reduce it as much as possible. As you can see here, this foam fractionator that we designed is actually capable of reducing at least 50% of the TSS, as you can see here. From 3,512 ppm, you can reduce to about 1,550. So if you have the feed coming in with a lower TSS, the membranes will, the rate of fouling for the membranes is going to be much reduced. So that's why we have to put a foam fractionator in front of the membrane before the waste enters the membrane system. As you can see the results down here, that all the COD values is also much reduced from 2,000, 2074 to 1,005, and so forth. For these are all for the different points, different wastewater from the cleaning tank, from the leaching tank, and from the cooling tank. So you can see now here that there is about 53% to 72% removal you can actually remove for the TSS. And the COD removal is about 23 to 38% removal. So our idea to use the foam fractionator to remove as much of TSS seems to be working quite well. So now what we do is that we then combine the foam fractionator and the membrane system to see what are the results like. Next slide, please. So now we know that our idea of using a foam fractionator works. So what we do now is actually we then optimize our foam fractionator. Foam fractionator we optimize. Why? By varying the pressure and the flow rate, and then we also analyze our foam fractionator process. We make some adjustments to the foam fractionator in terms of the water inlet point and the water outlet point. So we do some design experiments, statistical analysis to actually optimize our foam fractionator. Next slide, please. So, and of course, we measure the effect of pressure also. So these are some of the parameters that we actually vary. For example, you use our pressure. Our membrane is a low pressure membrane, so we don't actually use very high pressure. Our highest pressure is about 3 bar, 3 to 5 bar. We don't use anything that is more than 3 bar. So, but we tried 5 bar. 5 bar have slightly the results for 5 bar and 3 bar is not much different. So we decided that 3 bar is actually one of the best conditions to use for the membrane. Next, please. Of course, we also check on the cross flow velocity, and we vary some cross flow velocity so as to get some of the optimum points. So I'm not going to go in detail as to the what kind of statistical analysis we use. We use design experiments. Next slide, please. So these are the results of the optimization. We find that by optimizing, we can actually get better results. As you can see here, the results are much better here. Further reduction can be seen here. So this is the effect of optimization. And then we also optimize the form fractionator. Next slide, please. Okay, for the form fractionator, as you can see, we design it such that when we do some optimization, we redesign some of our form fractionator parameters, such as we put in some separator at the bottom here. So we have three different designs down here. One here is without a separator, one with a separator, and one with an inverted kind of separator down here. And we actually test for these three different designs, and to find which is the best design to be used when we are doing it, when we are doing the upskilling process. So we find that among these three processes, the second design here gives the best results because of the design of this form fractionator at the bottom here. What will happen is that we put in the fit here, and then we put in a small kind of a rotor down here to actually twist the flow rate, and then the micro bubbles rises up, and then the foam get collected at the top. And the results shown here shows that the second design here gives the best kind of design from the foam fractionation process. So this is done using our statistical analysis to get the best design, and also to get the best parameters of the length of the where to place our feet, height, and where is the collection point, etc. Next slide, please. So the results then, I think, of course, I'm not the one who controls the slide, so it's a bit different too. Okay, as you can see here, these are the two-factorial design. Probably we can just skip and then come to the quality of the water just now, please. The slides for that. Yeah, as you can see here, these are the kind of parameters that we obtain when we vary all these different flow rates. Next slide. Not this one. Okay, probably next. These are the screening factors. I think we just skip on this. Next slide. Okay. I'm not going to bore you with all these optimization parameters. Just probably you skip on this. So we do some optimization, and we find that we work on this region here with the maximum total solids removal and the total maximum protein removal. So finally, we find out that, probably next slide. So you find that by doing various optimization, we find that we can actually improve the whole process, and we work out and we find out what is the best kind of inlet flow rate to use, what is the best formate overflow rate, like the height that is to be used. So we have actually we optimize all the parameters that we use before we move on to a larger scale. Next slide, please. So then when we try to find it, so after optimization the foam fractionator conditions, after optimizing the membrane filtration, we find that, look here, we find that this is the one that with no pre-treatment, and this one is the results when we do a pre-treatment and we optimize the whole fractionator. So we find that, as you can see here, the flux here, before optimization, the flux can upon membrane fouling, the flux can be much reduced to about 15 meter cube per hour. After optimization, we find that even the minimum point is only about 38 meter cube per hour, if I'm not mistaken. So you find that the performance of the water permeate itself, it looks very good here. And then after cleaning up, we can get back to its original condition down here. So the optimization process has actually improved the water permeation of the membrane, and also has improved has reduced the fouling of the membrane. Next slide, please. So you can see down here, the fouling of the membrane here is very much reduced compared to without the optimization process. Okay, and the water accumulation is in fact better than previous results. All right, previously was like 14. Now it gets after optimization, you get better permit flow rate. Okay, right. So probably we can go to the one to the side, the slide before this, please. So by putting the pre-treatment as we have suspected, we can reduce foulants that can cause the blockage on the membrane surface. We can prolong the shelf life of the membrane, and we can maintain the membrane performance. Okay, so there's lesser flux decay. The total amount of fouling and irreversible fouling is also reduced. Higher permeate flux and more treated water being produced. All right, next. So the physiochemical analysis of the treated water, as you can see here, is also much improved. As you can see here, the pre-treated water, this is treated wastewater using optimized treatment process. So we find that after pre-treatment, once you pre-treatment, the pre-treated water passes through the membrane, you find that the fouling is much reduced, and also the results are much better. So this is pre-treatment coming out. This is filtered. You can see that the reduction here is much better. Okay, and you find that the reduction removal here is about 99% the TSS. BOD is about 95% removed and 97.4% removed. So that's for the water from the other tanks. Okay, the cleaning tank, in fact, the removal is very good. In fact, it meets the standard. This is standard A, I think. I think this is standard A and this is standard B. This is standard B and this is standard A. Okay, so we have met the standards A and standard B. Standard B quality of the water. We have met the quality stat for standard A and also standard B, and in fact, some of this water, the TSS content is being reduced so much that we can even recycle the water back into the system. Okay, so based on all these small scale results, we then move on to a larger scale results. Next, please. You can see here the results are very much improved. Previously was only 100%. So the conclusion for the small scale is that our nanofiltration membrane was able to actually treat the wastewater from this glove manufacturing industry, and the optimized membrane filtration was able to improve the permeate flux water production while minimizing the flux decay throughout the filtration process. And that's minimizing the fouling. I'm not saying that I'm going to remove totally the foulants, but we minimize the flux decay. And the content of the pre-treated water in terms of TSS, COD, and protein content is obviously reduced after subjected to such pre-treatment. And almost 81% of the TSS removal rate and 80.4% of protein removal rate is the highest removal, and is recorded and is obtained from this foam fractionation process under the optimum condition, about 27 liters per minute feed rate and 35 centimeters fomate overflow height. Okay, so there is very much significant improvement in the separation efficiency of the water quality obtained from the whole system under the optimum condition of 27 liters per minute flow rate and this height. So now what we do next is to upscale the whole process, and that's the interesting part of the whole process. Next, please. So for this final phase, we actually upscale. This is the lab scale that we did, right? Just now we did. So we upscale the whole process. So of course, the material that we use, we just in our small scale, we just take this polycarbonate filtration membrane cans. We get them, we cut into various size. We cut it and then we glue them together, assemble to a larger tower. But for a larger scale, you cannot do that. So what we do is that we have this acrylic tanks, okay, because we want to see what exactly happens in the foam fractionator. This is to give an insight to our industry people what is happening in the foam fractionator when we use it. So we cut the foam acrylic system into 3 sections here. One is the foam collector here at the top here, and one is the separation section here where we put in some mixer here, and the feed will come in somewhere in this region here. I do not see, you can't see here the feed here. And then you have the clean water collection section at the bottom here. So you find that the feed comes somewhere somewhere here. So there'll be separation will take place here, and then you find that the particles and the bubbles will form and then float at the top here, forming the fomate. the foaming is collected at the top here and the clean water here. Okay. And as far as the next slide, please. As far as this is a small scale membrane, so we upscale our membrane to a large scale here. This is a module bigger in size, about what? This whole system is capable of handling about 600 liters per minute, 600 tons of water per hour. So this system was actually initially built up last time to solve another problem of the flood problems. So it's a mobile system, so we can actually carry it. Although it looks huge, but we can actually disassemble it and carry it to where we want to actually use the membrane. Next slide. So what we did was after assembling in our plant. So next slide, please. So after assembling, so this is where we put in our foam fractionator. As you can see, this is the site that we install our foam fractionator. As you can see that we are working in a very small area because we are putting our foam in place of some of the current system that they have. So we put our foam fractionator here. And I have some videos, but unfortunately I cannot show it today to you here because I don't know what happened to my computer today. But anyway, so this is the feed coming into the system. As you can see here, this is our feed here. So this is a foam fractionation installation, which was actually at the third level of the building. So before we start the whole system, we have to make sure that there's no leaking in between the tower sections. So this is, as you can see here, this is being the installation process taking place. Yes, I have some photographs here. Next slide. So then, of course, we have to make sure we install some tanks so as to the feed from this tank will be then fed to the foam fractionator. So we have a holding tank here for the foam fractionator being placed next to the foam fractionation at the third level. It's a closer view. Okay, and then next slide, please. So working in the real environment. Real site is actually very challenging. Unlike the one that we do in the room, in the lab is very easy. But then now that we are in the system, you have to pump in, and the water, the waste effluent from the bottom, from the sump pit at the bottom to the third floor, because we can only get a space on the third floor. So initially when we handled the wastewater, initially was the wastewater that we collected from different points of the plant. But then when we go on site, the company insists that to take the water from different sites will be rather difficult because the space is very limited. So what they wanted us to do is actually to get the water from the central waste, which actually consists of wastewater from the leaching tank, wastewater from the cleaning tank, and all those and other wastewater that has been mixed up in the sump pit and then pumping up to the third floor. So we have no choice because we want to see whether the whole system that we are talking about actually works or not. So we basically assemble it according to what our client wants. Okay, so we basically assemble it. Next slide, please. So we have this holding tank being placed before the nanofiltration membrane. So what happened is that the output from the foam fractionator will be put into this holding tank, and then only then we'll pass it into our membrane. Next slide, please. Hello, next slide, please. So this is already the tank that is really ready for testing. So we have a leak test down here using water in the foam fractionator. We do the leaking test to ensure that no leaks are happening. Okay, next one, please. Now you can see that now this foam fractionator is already in operation. As you can see, when we pump in the water at using a centrifugal micro bubbler pump, we find that this is where the separation takes place, because it's like milk. It's latex. It's full of latex here. So this is the part where it separates out. As you can see down here, the water feeding comes at somewhere in the middle here. Okay, I can't show it very clearly. I have a video, but some other video, my slide doesn't work. But anyway, this is the feed. The feed comes in somewhere in the center here. And then this is the separation section. And you can see there the foam is actually taking place at the top here, the foam formation here. So the top here is actually collecting all the latex particles in the form of foam forming at the top there. And what you see at the bottom is the clean water that has been separated from the latex. So this water will then be pumped back into in the holding tank down here, ready to be put into your membrane system. Next, please. So I have some slides actually to show how when the nanofiltration unit is in operation, but I do not know whether, but because I couldn't, there's some technical problems, I couldn't show it to you here. Of course, and then these are some pictures on the foam because at the top there, when you have the foam, right, of course this foam needs to be broken off before and collected, okay? So the foam, after the whole process, we actually break the foam so that we can collect all the dirt out. So the foam totally breaks after some time. Otherwise, it will cause a lot of messiness a lot of mess also at the top there. So you have to make sure this foam is actually being cleaned off and then repeat the whole process again. Okay. Next. So finally, after we have run the installation run, so this is the kind of results from the foam fractionator. You can see there that this is the suspended solid that we feed to the foam fractionator. This clarifier is the kind of is the current process. They use the current process. After they pass from their water treatment process, this is the kind of treated water that they get after passing to the coagulation process, after passing to the clarification, and also the activated carbon. They get this kind of suspended solids. But then when we use our system fractionator, we call it a schema. Our foam fractionator is actually our schema. So we find that this is the kind of pre-treatment, this is kind of results that we get. We find that the TDS is actually reduced by half, about almost to 50%, and then our COD is being reduced also from 500 to about 413, and then turbidity is also reduced from 233 to about 26-24, which is actually, as you can see here, this is the feed and this is the output from the foam fractionator compared to the current system that they have. So which is actually a very the results are actually very, very very promising and very good. So then this water that we have here from the foam fractionator are then only fed to our membrane system. So we actually removing a lot of fouling problem. Fouling problem can actually be removed by using this foam fractionator, as you can see here. Okay, next slide, please. So this is, as you can see here, this is our raw wastewater. So we run, in fact, in order to actually reduce further fouling, we have actually done certain runs, and we have actually the clean water from the bottom of the foam fractionator, we actually do some recycling and find that after third round, you find that the water obtained is actually very, 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 very clean, and you find that the COD meets the standard B. As you can see here, the COD meets the standard B, the TSS also meets standard B, and the TDS, the COD also meets the standard B, which is less than 200. And you can see from the visually, in fact, you can see how clear the water is. Next run. So this is just from the foam fractionator, right? Next slide, please. So that's it. That is the results of the one of the pilot plant for, we consider it as a pilot plant. It's not huge really, but the results are very, very promising, as you can see here. I wanted, of course, to show certain slides, but unfortunately, due to technical problems, the slides cannot be seen. Okay, there's one complete system now. Now this is another result. I think this one we missed this slide. The final slide. Okay, as you can see here, this is the water the water from the skimmer are then being fed into our membrane system. So this is the water from the skimmer and then being fed to our membrane, and you can find the water that comes out from the membrane is definitely very clear. In fact, we put in some fishes, and fishes are actually swimming happily into the water. In fact, this water can best be recycled. So you can find here that we meet the standard A, not only the standard B, but also the TDS meets both standard A and standard B. As you can see here, it's less than 1,000, and the COD is less than 80, as you can see, and the turbidity is 10, and the SS is less than 50. So by passing it to a foam fractionator, it makes a difference. It saves the life of the membrane, and also you get very extremely clean water at the end of the whole process. So that's the end of my my presentation. And if there are any questions on the floor, I'm very happy to actually answer you. Thank you very much.
Alright, terima kasih Prof. Aini atas perkongsian tadi. Sekarang ni kita buka untuk sesi soal jawab. kita dah ada satu soalan daripada Facebook website saya, daripada Profesor Madya Dr. Zainul Akmal. Soalan beliau ialah, how crucial it is to involve industrial inputs during the development of processes at lab scale, and if it is, what developmental factors would it help to reduce?
It's a sticky question to ask. Okay, usually when you have industrial inputs, of course, the first thing to do is that you must ensure that your research project or the output from your research project has some stand that it can solve the industrial problems. So what you do is that you have to go to the company and pitch whatever that you have results from your previous experiments. For example, because when I started off my research, I studied on, of course, most researchers, they will study in the lab scale first. They do experiments on the lab scale, and they are hopefully to get, they hope to get very good results, and they start to publish. But publication is not the end of the thing. Okay, once you are able to publish the results, then the next thing you ask is that, is this applicable for industries? So once you are comfortable with the results, and you know that, for example, for membrane system, there are two things that is very important. One is the rejection rate of the membrane, which needs to be at least minimum about 88 to 90%. Or in fact, as high as about 95%. If you can reach that rejection rate, then you find that the next step is to look at the permeate. What kind of permeate rate you're talking here? We cannot have a very high rejection rate membrane, but very low permeate is about very few millimeters dripping out coming from your membrane. So that's not functionable. So once you feel that your results are good and you have actually patent, then that's where your confidence comes in to go to industries and look and say, I have this particular product, and I'm very sure that I'm confident I might be able to do something for your industry. Okay, so what we do is that we have to pitch to industries, of course. For this particular project that I've got is through a pitching process, and the industries seem to be very attracted to the membranes that we have. So what they did was they actually fund the whole project. So it was a 240,000 ringgit project. They funded out, and in fact they also fund the master student that was doing the project. So this is one of the projects whereby it's very satisfying because we have a student running the whole project and we are there to monitor the whole project. So we cannot just do on a larger scale because we don't know whether it works or not. So what we do is that we run the small scale system first, and when you want to run a small scale, in other words, we have to bring the water samples from their side back to the lab to check, see whether the quality of the water that they want can be achieved using our design systems. So once you are happy with the small scale, then you go up and say, look, these are the results of the small scale, and I believe that if you were to upscale, it will work out for your system. So that's when the upscaling part comes to the picture. And then once you're happy with it, on the upscaling, then we bring it to site and test the system on site. So the involvement of industries is very important. In other words, you want to get the water from them. Of course, these industries are also very, very secretive because they don't want you to actually probably tell what kind of waste they're having, So but then by having the confidence that, okay, look, I have this, let me give it a try, then they are willing to come to you and actually do it. And also with the government introducing the double tax deduction, so that is also an attraction to the companies to actually come to us, work together with the universities to actually do projects. And in fact, the student is now working in the company also.
Okay, alright. Terima kasih Prof atas perkongsian dan juga sedikit tips untuk penyelidik yang ada hadir pada hari ini. Since kita dah sampai ke penghujung, I think dah almost pukul 11 sekarang ni. Saya rasa dah tak ada lagi sebarang soalan daripada penonton, dan dan saya nak wrap up sedikit lah kepentingan perkongsian pada hari ini, which is nanofiltration membrane adalah nanofiltration membrane penting, dan I think dia boleh membantu industri untuk satu treatment yang lebih sustainable dan juga low cost yang rendah, memberikan kos yang rendah kepada industri, which is sangat membantu dalam satu proses sebuah proses dalam industri lah. So I think saya akan akhiri webinar pada kali ini, dan terima kasih diucapkan kepada Prof Ani kerana sudi berkongsi pengetahuan dalam bidang kebakaran beliau. Dan untuk penutup ada juga sebuah pantun untuk semua. Di atas dahan burung tempua, melihat rusa tepi perigi. Terima kasih untuk semua. Lain kali kita bersua lagi.
Thank you very much again from me. Thank you very much. Bye.